So, welcome back to this course on blockchain and its applications. So, till now you got a fairly good understanding about what blockchain is in what are the different use cases of blockchain, and you have learnt about two broad blockchain platforms, the permission blockchain architecture and the permissionless blockchain architecture, and you got a demonstration and tutorial of both the platforms. From the permissionless domain, we have seen the Ethereum architecture, and you have learned that how you can develop your decentralized apps or dApps using Ethereum. On the other hand, for the permission blockchain model, you have learned about Hyperledger Fabric, and you have seen that how you can build up your own DLT platform or your own DLT application using Fabric. So, with that we got an understanding about the basics of blockchain and how the blockchain can be applied or how you can build up your own applications using blockchain. So, from this lecture onwards, we are going to start with some advanced topics on the design and implementation of blockchain. We are going to look into few of the important aspects of blockchain which are very much important to consider while designing a blockchain platform as well as an application on top of blockchain that you can consider while building up your own applications or own service. So, we will look into different aspect of it, and today we will start with consensus scalability. Today we will discuss a bit about what is meant by consensus scalability and why scalability is a problem for blockchain and what are the different ways we can solve it. And in the next few lectures, we are going to learn about that how you can make a blockchain scalable and what are the different innovations that have been done by the different cryptographer researchers across the globe to scale up the blockchain based applications. And then we are going to learn about different other advanced topics in the domain of blockchain like the interoperability, identity management and so on. So, let us start today with this discussion on consensus scalability. So, broadly we are going to talk about blockchain scalability in this lecture, and in subsequent lecture we are going to look into different protocols and architecture that can be applied to scale up a blockchain platform. And in terms of keywords, today we are going to look or we are going to do a kind of comparison between proof of work and the PBFT consensus mechanism. And as you already know that proof of work is the consensus for a permissionless model of blockchain, where PBFT is the consensus model for the permission model of blockchain. And then in that context, we are going to learn about the scalability and the scalability requirement for the consensus models, the blockchain consensus model. And finally, we are going to touch about something called consensus finality and why that is important for the design of enterprise applications or the enterprise blockchain model. Now, to start with, we have learnt about the different type of blockchain consensus protocols. We have learnt about the permissionless blockchain architecture, and in the context of permissionless blockchain architecture, we have seen different consensus algorithms like the proof of work, proof of stake, proof of burn, proof of elapsed time and so on. And what we have seen that proof of work is something that really require computation power and that require participation from a large number of miners, where the miners try to solve a complex problem in a decentralized way to find out a solution against a challenge provided by a network. And once you are able to find out that challenge solution of that challenge, you can propose a new block and that block gets added to your system. Then we have seen that because of the limitations that proof of work has in terms of resource consumption, we propose or people proposed different type of consensus algorithms like proof of stake or proof of burn, where you can use the digital assets to participate in the mining procedure. But interestingly, what we have seen earlier that this proof of stake or proof of burn, this kind of algorithms actually depends on proof of work. So, you cannot bootstrap your system with proof of stake or proof of burn. You need to start with proof of work and gradually you can migrate to proof of stake or proof of burn. And then we have the independent consensus models like the proof of elapsed time that was particularly proposed by Intel, and that was a part of the hyperledger sawtooth architecture. But we have seen that for proof of elapsed time you need specialized hardware like a trusted execution environment. So, for Intel platform you can possibly use Intel SGX to use this proof of elapsed time. So, that way we have different kind of consensus model for the permissionless model, the permissionless blockchain, and in the similar way we have seen that for permission model we have broadly these Byzantine agreement protocols or different types of Byzantine agreement protocols. We have learned the details about PBFT, practical Byzantine fault tolerance architecture, but apart from PBFT there are different other Byzantine agreement model like RBFT, the hybrid BFT and so on, which we have not covered in details, but people have developed that or people have analyzed that to speed up the execution of PBFT. So that way also in case of permission blockchain model we have taken help of the classical distributed consensus algorithm, and we have used that classical distributed consensus algorithm along with digital signatures and other cryptographic primitives to apply them on top of the blockchain architecture. So, the popular blockchain platform like Hyperledger Fabric, as you have seen earlier, it uses PBFT as a consensus model to reach consensus among different parties in terms of proposing a new block. So, that way we have learnt about different kind of consensus models, but if we try to do a kind of comparison between all these consensus models, let us see that what we get. So, that is basically our discussion today in this particular lecture. So, if I just compare between proof of work and PBFT, so in proof of work we have seen that it is an open environment. It works over a large number of nodes. So, anyone can join in your proof of work system. They do not need any kind of pre-authentication or pre-validation. So, from that perspective, whatever we see that proof of work is scalable in terms of number of nodes. You can really have millions of nodes in your system who can participate in the proof of work based system, but the transaction throughput is pretty low. So, today in this lecture we are going to have a mathematical computation about what is the typical transaction throughput in a proof of work based system, but what we broadly see that the transaction throughput for proof of work is pretty low. On the other hand, if you consider PBFT or the Byzantine agreement protocols in general, they work over a closed environment because they are relying on message passing, and as we have seen earlier that message passing is something that actually create a burden for an open environment. So, in an open environment when you do not know who are the participants in your system, you cannot use a message passing based interface, and whenever you cannot use a message passing based interface, you cannot use the classical distributed system consensus models like the Byzantine agreement protocols. But in case of permission model, because you are mostly working on a closed environment where the identity of the participants are known, and because the identity of the participants are known, you can run a message passing based consensus model, and that way the Byzantine agreement protocols are much more popular for a permission model of blockchain that we have seen. So, this PBFT is working over a closed environment. Because it is relying on message passing, it is not scalable in terms of number of nodes, but on the other hand it provides high transaction throughput because it is depending on the message passing. So, that way you do not need to involve or you do not need to invest a huge computation power to compute the hash or to compute the solution of the challenge, and that way you have you can reach to a consensus in a much more less time compared to what is being supported by proof of work. Now, if I just try to look into the scalability of proof of work, well, so this is something an interesting calculation that we are going to do now. So, there are two magic numbers in proof of work, one is the block frequency, another one is the block size. So, this block frequency tells you that how frequently you can mine a new block, and typically in a proof of work based system or a Bitcoin proof of work kind of architecture, your default block frequency is 10 minutes. So, that means that every 10 minutes a miner can mine a new block. So, once a block is mined, then after 10 minutes you can mine the next block. And it also provides an upper bound on the block size. So, historically for Bitcoin this upper bound was 1 MB. So, later on it increased to 4 MB and then 8 MB. But currently that 8 MB is something the maximum block size that you can support, and this bound on the block size is typically depending on that how much time peer required to download the newly mined block, because once a new block has been mined, say if you are a participant in the blockchain network, you need to download that new block to your local copy, right. Now, if you increase the block size, then obviously it will take a lot of time to download that new block. Well, and if it happens to be that by the time you are downloading a new block, another block gets mined, that will create problem for you. Well, so that might create inconsistency in the network, and the system might find out that well it got the next block, the previous block has not been downloaded. So, that way different kind of inconsistency might come, and that way you need to ensure that well the maximum block size is such that you can download, or all the peers in the network can download that block before the next block gets mined. Well, and that way by analyzing all these things, the current delay distributions in the network and all these different parameters, the developers of the Bitcoin blockchain, they have limited this block size to 8 MB. Now, for Bitcoin, let us try to do an calculation. Let us try to do the calculation with a simplistic assumption. First, let us assume that the block size is 1 MB. That means the historical Bitcoin. If you just go to 8 MB, you will find out the updated transaction throughput. That will again you will see not much more. So, if your block size is 1 MB and the average transaction size typically including that Bitcoin script. So, the transactions that you have seen in the Bitcoin block explorer, those transactions where I am sending certain Bitcoins to you, this kind of transaction has a typical size of 380.04 byte. So, that contains the general scripts, and that scripts including the size of the transaction data as well as the scripts, it becomes something around 380.04 byte. Well, now for different transactions this size is different, because as you understand that the script will be different, entities which are there in the transaction that will be different, and that way the size would differ, but this is something like average transaction size depending on all the transactions that we see in the current Bitcoin blockchain. Now, if you just assume that your block size is 1 MB and average transaction size is 380.04 byte, so you can find out the number of transactions per block as the block size divided by the transaction size. So, your block size is 1 MB. So, if you convert it to byte, it comes to be 1048576 byte, and your average transaction size is 380.04 bytes. So, the average number of transactions per block is approximately 2759.12. Well, so this is one number that we get which tells me that what can be the average number of transactions per block. Well, so that we get by assuming the block size to be 1 MB and the average transaction size to be 380.04 byte. Now, with this if I just try to see that within 10 minutes that is my block mining time, as we have mentioned earlier that the block frequency is 10 minutes for a typical Bitcoin blockchain. So, with 10 minutes means 600 seconds, that means you can commit approximately 2759.12 transactions in 600 seconds. Now, with that if you just try to calculate the transaction throughput, that means the transactions per second that is being supported by Bitcoin blockchain with a maximum block size of 1 MB, it comes to be something around 4.6 transactions per second. Well, now if you just look into the number of transactions that is being supported by typical platforms like Visa. So, Visa supports around 1736 transactions, that means 1736 transactions per second, and you can just see the gap between Bitcoin and Visa. Well, so even if you think that well I will use Bitcoin for financial transaction, by looking into these parameters you can be sure that well it is going to be a nightmare if I want to support the level of financial transactions that we do with the help of Visa nowadays. Well, for Bitcoin it is 4.6 transactions per second, whereas for Visa it is around 1736 transactions per second. Well, so obviously the question comes that how I can scale up, how I can increase this number of transactions that can be supported for Bitcoin. Now, as I have mentioned that there are two magic numbers that we have, one is this block frequency, another one is this block size. Well, so we came to this 4.6 transaction per second with these two parameter. Now, let us see that if I just try to tune these two parameter, what happens. So, which parameter setup we can reach towards something that is being supported by Visa, that means around 1736 transactions per second. So, this is a table that I have taken from this particular website, which talks about which provides a nice article about this blockchain scalability. So, what it did that it tried to tune these parameters and tried to find out that well what should be my block size or what should be my block frequency with which I can reach a transaction throughput or transaction per second equal to 1736 transaction per second, which is typically supported by Visa. Well, now the default thing what we have seen is like 4.6 transactions per second, right, where I have 1 MB as the block size and I have 1 MB as the block size and I have this 10-minute or 600 second as the time for committing a block. Well, now let us assume that I want to have a transaction per second, that means TPS equal to 736, that is equal to Visa. Well, what I do that I keep the block commitment time same. Well, so block commitment time same means I keep the block commitment time as 600 second. Now, with that if I try to find out that for which particular block size I should be able to reach to transaction per second, that means the transaction throughput as 736 transactions per second. If you do that calculation, you will get a number something like this 395,808,000, which is something equal to 377.5 MB. Well, so that means if you make your block size equal to 377.5 MB, then you can get a transaction throughput which is equal to 736, that is being provided by Visa. Now, we have the problem. So, what is the problem? So, the problem is that if you make your block size equal to 377.5 MB, then that typically means that once a new block gets mined, every peer need to download 377.5 MB of data. Well, and if you just think of that, well, you are in a slow network where your download speed is possibly something equal to a few hundred kbps. Now, with that download speed, downloading 377.5 MB of data is something like a nightmare. Well, so it will take a lot of time to download that much of data. Now, by the time you are downloading that much of data, immediately your next block will get mined. Well, and again you need to download some data. That means you need to continuously download a huge amount of data to support this much of transaction, which is practically infeasible and practically infeasible for the peers who are having slow network connectivity. So, with this let us try to tune the other parameter. What was my other parameter? The other parameter was block frequency. So, again I want to get transaction throughput equal to something being provided by Visa, that is 736 transaction per second. Now, this time I keep my block size as 1 MB, but I tune this parameter which is the block generation time. Well, so earlier it was 10 minutes, that means equal to 600 second. Now, if I just try to compute that for which block generation time I can get a transaction throughput of 736 with 1 MB of block, we can get a value equal to 1.589. Well, so something close to 1.6 or 1.5 second. That means at every 1.5 second you need to mine a new block. Now, to mine a new block within 1.5 second, you can think of that you need to reduce the complexity of this challenge of the hash significantly, right, because the miners need to quickly find out what is going to be the hash, what is going to be the value of the nonce. Well, and if the miners need to find out that value of the nonce within 1.5 second, that means that challenge need to be much more easier. And if I make the challenge much more easier, then obviously I am compromising with the security of the system. Well, so that means this is again infeasible to make a transaction through commitment time or block generation time equal to 1.5 second or 1.6 second, something in that order. Now, what we do that, well, let us try to make it something like 14 second. Well, so I am making the transaction throughput as 14 second. So, when I make the transaction, sorry, not the transaction throughput, that block generation time as 14 second. So, when I make the block generation time as 14 second, I keep my block size as 1 MB. So, I get a transaction throughput of 197.1, okay, which is again much less compared to what is being required for Visa, but well, it is much more higher compared to what is being supported by default. That means, it is much more higher compared to 4.6. Well, now if I just want to double the block size, well, so this is again interesting. So, if I double the block size, that means, if I make the block size from 1 MB to 2 MB, again I need to also increase this block generation time, because if I make the block size larger, I need to, or if I double the block size, to download the data, that also gets doubled up. Well, so this 14 second is a typical time that is taken by for downloading this 1 MB of data with a standard cellular network connectivity like a 4G. Well, so if I double up the block size, this time will also get doubled up. So, this will become 28. Now, if I double the block size and double up this time, block generation time, you see that my transaction throughput comes to be 196.6. So, not much difference between these two. Well, so that means if I need to increase the block size, and if I provide minimum time for generating that block, then with the increase of this block size, that time also increases proportionally, and as that time also increases proportionally, I do not get any gain in terms of transaction throughput. Now, from all this discussion, what we understand that there is a limitation of the transaction throughput that we can achieve on Bitcoin blockchain with proof of work based system. Well, so we cannot increases it unilaterally, or we cannot make it equal to Visa. It is practically impossible to make it equal to Visa. But the question comes that how we can get a kind of transaction throughput which is good. Well, now this is again one of the pioneering paper from Marko Vukovic that actually tried to compare the different kind of consensus protocols in terms of performance and scalability. So, this x axis shows the node scalability, that means the number of nodes that is being supported by the corresponding consensus algorithm, and the y axis shows the performance. So, the y axis indicates that what is the transaction throughput. So, the minimum transaction throughput is less than 100 transaction per second, and the maximum is something more than 10k transaction per second. Now, if you look into the BFT protocols, the BFT protocol somehow resides here. Well, so this BFT protocol, they provide very good transaction throughput, okay, in terms of performance, but their scalability is much less. So, typically they work less than 20 number of nodes or sometime in between 20 to 30 nodes in that range. Well, whereas if you just look into the proof of work based system, these proof of work based systems are at the other end. Well, so this proof of work based systems is something that supports large number of nodes, but they provide less transaction throughput. Well, so ideally we need something at this space where I can have large number of nodes and at the same time I can have significantly higher transaction throughput. Now, the question comes that how we can design such a system. Now, to design such a system, let us try to make again a comparison between proof of work and PBFT. So, this time we are comparing them in terms of consensus finality. So, Marko Vukolik in that particular paper, he has given a nice definition of consensus finality. So, what is meant by consensus finality? So, if a correct node P appends block B to its copy of blockchain before appending block B prime, then no correct node Q appends block B prime before B to its copy of the blockchain. Well, so that means if I have two blocks B followed by B prime in a blockchain, then all the correct nodes will follow this sequence. Okay. Now, in case of proof of work, we have seen that this is not supported, well, because I have fork. So, whenever I have fork, I might have two different blocks which are pointing B, say B prime and B double prime. So, it might happen that well for some nodes in the network where the network got partitioned because of this forking, they are using B double prime to point to B, whereas some other nodes, other peers, they are using B prime as the next block after B. Well, so that way proof of work does not ensure consensus finality, whereas these Byzantine agreement protocols like BFT, they ensures consensus finality, that we have already seen. Now, if I just try to compare this proof of work consensus versus BFT consensus in different other parameters, we have done a similar type of comparison earlier as well. So, this comparison is from the paper from Marko Vukolik. It uses multiple different parameters to do this comparison. So, in terms of node identity management, so for proof of work it is open, entirely decentralized. In case of BFT consensus, it is permission. Nodes need to know the IDs of all other nodes because we are using a message passing based consensus. In terms of consensus finality, proof of work does not provide a finality, whereas PBFT or BFT consensus provides a finality. Scalability in terms of number of nodes is excellent for proof of work, but it is limited for BFT consensus. Scalability in terms of number of clients is excellent for proof of work consensus, and it is also excellent for BFT consensus, both supports millions of clients. If I look into performance in terms of throughput, that means transactions per second, that is limited for proof of work consensus and that is excellent for BFT consensus. In terms of latency, proof of work has high latency because you need to mine a block, whereas BFT consensus has excellent latency, it supports with network latency. The power consumption is very poor for proof of work, as we have seen earlier. Proof of work waste energy, whereas it is good for BFT consensus. If you just look into the adversary power, the power that an adversary can have for the safe operation of the blockchain, in case of proof of work it is less than 25% of the computing power. In case of BFT consensus, it is less than 33% of the voting power. In case of BFT consensus, you have seen that if you have f number of faults, you need at most 3f plus 1 number of nodes in your system. So, that way the adversary can have less than or equal to 33% of the voting power. If you think about the network synchrony assumption, proof of work consensus works with physical clock timestamp, but BFT consensus does not consider network synchrony. So, it works on an asynchronous environment, but as we seen earlier for PBFT, that synchrony is required for ensuring liveness for the view change protocol of PBFT. Proof of work do not have any kind of formal correctness proof, but PFT consensus that has formal correctness proof. Now, in consensus, in terms of this consensus algorithms in blockchain, as we have seen earlier and tried to compare between proof of work and PBFT or the BFT consensus in general, what we see that scalability is a major issue in blockchain consensus, whereas the consensus for the permissionless model, they have limited transaction throughput, whereas the consensus model for the permission blockchain that use the Byzantine agreement protocol, they are limited in terms of number of nodes they support. So, that way we need to develop a consensus mechanism which is something that balance between these two, balance the transaction throughput as well as the number of nodes. So, in the next lecture we are going to discuss about the different kind of scalable blockchain protocol. We are going to see that how the researchers have typically tried to find out a balance between the transaction throughput and the node scalability. So, that is all for this lecture. Thank you all for attending this lecture. In the next lecture, we are going to discuss about the different mechanism or the different protocols for ensuring scalability in a blockchain. Take care.